So yeah, jokes, no jokes. Okay, so 72.3. Integration of conservative vector space. Integration of conservative vector space. Why should I tell jokes anyway? You can do something like this. Okay, so just remember, let's start off by remembering some definitions. I think this last section maybe is not as hard as I make it out to be. It's just you have to keep everything straight, right? It's just a bunch of calculations. You just have to remember what the calculations are. So let's remind ourselves what the calculations are. Okay. You have a function, and you have a curve. You're integrating a function against arc length. Okay. What is that? Does anyone remember? You have a curve. To get this sort of thing, right, you need to have a parameterization of the curve, A, B. So here's your curve, and you're integrating some function on that against arc length. You have some parameterization of that curve, right? And in that case, once you get your parameterization, then you can do this calculation. What's the calculation going to end up to be? Does anyone remember? No. Right.
Function evaluated at R
function
times R prime.
R prime T
dd or dt
dt
from A to B.
from A to B, almost
Magnitude of R prime.
magnitude of R prime, right? Magnitude of R prime, because remember R is a vector, right? R is a vector. R prime is the tangent vector. It doesn't make sense to integrate this. This is going to be a number, and you're going to have this vector. If you didn't have that in, you would end up with some vector value, right? You would end up with some vector value as your result. Okay, great. Right. Right. Or to put it into English, right? You take the value of the function at a point on the curve, and then multiply it by the speed of the curve at that point times the change in time. Right? In other words, the change in distance. Right? This is the infinitesimal. Right? This thing here is the instantaneous speed. Instantaneous speed. Right? This thing here is your infinitesimal amount of time. Right? And then so the speed times the change in time is going to be your distance. Right? So you take this distance traveled, right? The arc length, right? The change in distance, and you multiply it by the value there, and then you get that thing. Okay. So that was one thing. The other thing that we talked about was f, the integral of a vector field over a curve. Right? The integral of a vector field over a curve, which we defined as the integral of some function. Right? The function was the. Do you guys remember? T, right? You integrate the function of the field dotted against the unit tangent vector, right? And you get this, right? Which, if you use the definition above, turns into A, B, F, F dot T, right? Well, what's T? T is the tangent vector divided by its magnitude, right? So this is F dot, this is the function, right? And then we're going to multiply by R prime, T is magnitude, dt. This is our function evaluated at R of t, and you get that. And you see what happens, that you get this cancellation, and it turns out to be, f at R of t dot R prime t dt, right? Justifying the notation. Okay, so this was the definition. This was our definition, and then this is what it turned out to be if you're calculating it. Okay. So just to remind us what the terms are, and there's going to be more and more terms as time goes on. Okay. Okay. So so the question that we're going to deal with today is what happens if we're dealing with conservative vector fields? Okay. So what if the field is actually the gradient of some function, right? Okay. And so we can work it out. Here's the theorem. Given some conditions, R of t as t goes from A to B, a smooth parameterization of a curve C, and given a function, a differentiable function with the gradient continuous on C, then if we calculate the integral of that gradient vector field, we calculate if your vector field is the gradient vector field and you calculate the integral over a curve, it turns out that you get f at one endpoint minus f at the other endpoint. You get the potential function, well, not exactly the potential function, you get minus the potential function evaluated at the endpoints, the difference at the endpoints. Yeah, Melissa.
This is kind of going back a little, but
sure.
For those two,
yeah.
Can you say what the name of each one would be? The first one is with respect to arc length.
Yeah, so this is the integral of a function. This is the line integral of a function with respect to arc length.
Okay.
This is the line integral of a vector field over a curve.
Okay. Thank you.
Okay. Okay. So, right. So, what does this remind you of? This should look kind of reminiscent of something. Fundamental theorem of calculus, exactly. Right. You're integrating some sort of derivative, and it turns out that the integral of the derivative, the definite integral of the derivative is going to be the function whose derivative that is evaluated at the endpoints, and you take the differences. It's a fundamental theorem of calculus. And indeed, the way you show it is by using the fundamental theorem of calculus. So you say, okay, well, just calculate it. Right? This thing here, dr, we just said, is going to be the integral from A to B of the function evaluated at R of t dot R prime t dt. But that turns out to be the same thing as the integral of the derivative of f composed with r at t dt. We had the chain rule. You have this composition, right? F composed with r, right? Going from r to r. Then the derivative is going to be the gradient of this dotted against the tangent vector of this. And then we use the fundamental theorem of calculus, right? That we're integrating this derivative, right? And so we get f composed with r t, as t goes from a to b, which is what we just said it was, right? It's going to be f at r of b minus f. Okay, so it's just a calculation. Calculation plus, the chain rule, right? So this is by the chain rule, right? And then this is by the fundamental, your old one variable fundamental theorem of calculus. Okay. Questions about the theorem? Questions about the theorem? Right. It says that if you're integrating this field over this curve, then all you're going to get is the difference of f at the endpoints, right? So, for example, when we had the gravitational field, right? F of x here was the function. We saw earlier that this function, if you differentiated, if you took its gradient, then you got the gravitational field. Right, the gravitation. So earlier. If you take f being this, then the gradient is going to be the gravitational field. Right, exerted by some large mass at the origin, right? Exerted by a mass m at the origin on a mass little m at xyz. Okay. And what we're saying is that if we take any 2 points in space, this was a G, looks like a Q. If you take any 2 points in space, x naught, y naught, z naught, x1, y1, z1, and this is the funny part. If you take any path c, right? If you take any path going from the first point to the second point, and you integrate the gravitational field against over that curve, well, all you're going to get is the original function evaluated at the endpoint minus the original function evaluated at the starting point. No matter what path you take, right? No matter what path you take. Right. Okay. So yeah. So the integral depends only. This equals f at x1, y1, z1 minus f at x naught, y naught, z naught. The integral depends only on the endpoints. Okay. So what our theorem tells us is that, for any conservative field, the integral is going to the integral of that field depends only on the endpoints. Okay. So we have a term for those guys. So we have a term to describe that kind of field. If f dot dr over c is dependent only on the initial and terminal endpoints, terminal points, then we say that the integral is path independent we call f a path independent field. So the theorem that we just said basically says that if f is conservative, then f is path independent. Okay. In fact, there's a converse statement. In fact, if f is path independent, it's possible to see that f is conservative. You have to put some conditions on. F has to be continuous on an open path connected region. If you're dealing with vector fields on open path connected sets, then the converse is true. That if f is path independent, then it is conservative. Right? So if it turns out that your integrals only depend on the endpoints, then it turns out that your field must be a gradient field, must be the gradient of some function. Okay. We're gonna skip the proof. If we have time, maybe we'll do it. But I don't think the proof is that. It's a little intricate. Something a bit easier to explain is the following. A vector field f is path independent if and only if the integral of the field is 0 for all closed paths C. So that is being path independent means that if whenever you integrate over a closed curve, and by a closed curve we mean a curve that that ends at the same point that it begins, then your integral is always going to be 0. Okay. Okay. So let's let me give you the argument for that. I hope I can give you the argument. So suppose your field is path independent. Okay, so say f is path independent. Okay. In that case, the integral depends only on the endpoints. Now say that C is a closed path. Suppose you have this curve and it's a closed path. Okay, we're going to try and see that that the integral over that path has to be equal to 0. Yeah, actually, I'm looking at the argument I have in my notes. It looks like it's wrong. So I'll put up the argument and I'll let you see where it's wrong. Okay. And then after that, I'll try and think of something that's actually right. Okay. While we're doing that, let me think of something that is actually right. Okay. Okay. So suppose this thing is a closed path, right? Okay. So you have this thing that's a closed path, like this. Say. And let's break it up into two parts. So so here's the let's break it up into two parts: C1 and C2. Okay. Take your path and then break it into two parts. Okay. Then the integral of C, the integral over the whole thing, is going to be the integral of the first guy plus the integral over the second guy. Right? That's certainly true. So far, so good. Right? Okay. But then, but if we look at the integral of f over negative C2, right? The integral of f over negative C2, so let's reverse C2 and have it go in the opposite direction. Okay. Then that guy has the same integral. Oh, actually, this actually works. Okay, sorry. Okay, then that will be the same as the integral over C1. Why? Negative C2 is in the opposite direction, right? So it's just C2, but going in the opposite direction. Okay.
But did you say that they're equal? Like,
I'm saying that
C1 and
the
C2
integral of f over negative C2 is actually the integral of f over C1. Why is that?
Well, are C1 and C2 like divided exactly in half?
It's all you've done is you've taken your curve and then you split it into two parts, C1 and C2, like this, so that when you traverse both of them, then you complete the circuit of C.
Oh.
Okay. Yeah, Paul first.
Well, f is path independent, therefore its endpoints don't depend, or the value of its integral don't depend on the path taken, only
Right.
on the endpoints.
Only on the endpoints, and these guys.
They share endpoints. It's
Exactly.
just they're going in different directions.
Yeah,
So.
yeah. They're not. In fact, they're not going in different
Or
directions. Right. Negative C2 is going this way.
Right.
Right. So they are paths with the same terminal point and the same initial point.
Yeah, once you reverse it.
because, right, since f is path independent, right? Right? But we know that the integral of the vector field over CR is negative the integral over negative C2, right? The integral over negative the field, I'm sorry, the integral over negative the curve is negative the integral of the original curve, right? Because you've reversed the direction of the tangent vector. Right? So what does that tell us? That, so going back to here, the integral of f dr is the integral over C1 plus the integral over C2. But the integral over C2, the integral over C2 is negative, right? The integral over C2 is negative the integral over negative C2. And the integral over negative C2 was the integral over C1. And so we get 0. Right. Let me call this observation star. Let me call this observation double star. So at this point, we use star. And at this point, we use double star. Okay. So whenever your field is path independent, then you know that it satisfies this closed curve condition. Integrals over curves are always going to be 0. Any questions about that? Any questions about that? I think we're going at a pretty good pace. So if you feel free to ask questions. Yeah. Any questions? No? Straightforward. Okay. Let's go in the opposite direction now. Suppose you know that you satisfy this closed curve condition, that the integral over any closed curve is 0. Well, let's see that makes it so that the integral over any paths that have the same endpoints have the same integral. Okay, right? So suppose the integral of f dot dr over C is 0 for all closed curves C. This is what's called f satisfies the closed curve condition. And we want to see that y then is f path independent. Y then is f path independent, right? Y does the integral not depend on the path, but only on the endpoints, right? The question is basically why then, if two curves C1 and C2 have same initial and terminal points, must the integral over C1 equal the integral over C2. Why is that going to happen? All we know, what we're given is that the integral over a loop is going to be 0. Why does that force integrals that have same endpoints, same initial and terminal endpoints, to have the same integral, to have the same value. I'll let you think about it for a minute. See if you can come up with something.
You set up 2 classes and then you go to the next point. And then you look. My circle is 0 and you set up 2 terms. And then adding them together has to equal 0. And so that means they have to equal each other. That's algebra. We do that with things.
Anyone have ideas? Yeah, Flo.
So the integral over C equals the integral over C1 plus the integral over C2, but that equals 0. So we know that C1 has to equal C2 if C1 plus C2 equals 0.
So, say it again, Flo.
So the integral over C equals
What is C? So C is
the full curve.
okay. So right now
C equals C1 plus C2.
okay. Let's see C1 plus C2. So here it is. Suppose this is C1, and suppose this is C2. Right, they both have the same initial and terminal points. Right? And you're letting C be C1 plus C2.
Or C probably equals in C1 plus minus like negative C2.
Okay, C1
Minus C2.
plus
Let's say that.
negative C2. No, that's actually maybe more legitimate to say that. Plus minus C2, right? So minus C2 is going to be going the opposite direction. Okay, so then C is a closed curve, right? And we know that we've assumed our function. For our functions, our field's integral over closed curves is 0, right? Right? And so the integral of C, which is the integral of C over C1 plus the integral over minus C2, right? Here's where the plus minus really makes sense, right? It's going to be 0, right? And you see what happens, right? The integral over minus C2 is actually the same thing as minus the integral over plus C2 by what we said last time, right? Those questions that stymie some people, right? And so the integrals, the integral over C1 must equal the integral over C2, and so you're path independent. Any questions? Right. This thing is the same statement as this one, right? Because you're integrating over C means that you integrate over the first part of it and then the second part of it, right? And then this is true because the integral of a vector field over a path going in the opposite direction is going to be minus the integral of the vector field over the path in the positive direction. And so we get their difference is 0, and so these integrals must be equal to each other, right? And so what we see is that if you have any two curves with the same initial and terminal points, then their integrals are equal to each other. In other words, your field is path independent. So pretty simple, right? These arguments are you know short and sweet. Okay. A couple more simple observations. We're sort of skipping all the. We're shoving under the rug all the tedious observations. Suppose you have a field P of xy, Q of xy, and it is a conservative C1 vector field. Right? So it is the gradient of some function. Right? It's the gradient of some function, and it's C1. Right? Then the partial of P with respect to y is equal to the partial of Q with respect to x. So this is a way of checking if a field is conservative, or rather is not conservative, right? Because you take the derivatives, of these component functions, and if they're not equal to each other, then you know that your field wasn't conservative, right? If it's conservative, then this is going to happen. If this doesn't happen, then you know your field wasn't conservative, right? But at this point, we don't have anything that says something is conservative. We only have a tool that says something's not conservative. Right? Is that clear? If it is conservative, then this is going to happen. If this doesn't happen, it must not have been conservative. Okay. So, so this gives us a way of checking if a field is not conservative. Can anyone tell me why this is going to happen? Why would the partial of the first one with respect to y have to equal the partial of the second one with respect to x? If your field is conservative. And so f is conservative. Right? Why does that force the derivative of the first guy with respect to y to be equal during the second component with respect to x? Well, being conservative means that, i.e., f is the gradient of some function. Okay. What does that tell you? Thus, p is going to be the partial of f. What's p? Partial of f with respect to x. Q is going to be the partial of f with respect to y. Right? And then what? P is partial with respect to y.
And if you do that with respect to the next one.
Right.
So x, y, and y x.
Right. So P's partial with respect to y is going to be fxy. Q's partial with respect to x is going to be fyx. Right. But if this is a C1 vector field, then that says that the function has continuous partials up to the second order. Okay, and having continuous partials up to the second order means that you can invoke Clairaut's theorem, which says that the mixed partials will have to be equal to each other. Right? So by Clairaut's theorem, note that f has continuous partials up to the second order. By Clairaut's theorem, we know that the mixed partials are equal to each other. Right? And so the partial of p with respect to y is going to end up being the partial of q with respect to x. Okay. Right. So at this point, what we have is that so if dp dy does not equal dq dx, then we know that f is not conservative. Assuming f is a C1 vector field. In fact, something, the opposite statement is also true, right? We have something that gives us a partial converse. So if f is a C1 vector field on an open, simply connected region, D, if the partial p with respect to y equals the partial q with respect to x throughout D, then, in fact, f is conservative.
Simply connected?
Yeah, I haven't explained it. So what does simply connected mean? Is that what you're going to ask also, Lily?
No.
No.
I was gonna ask, so like this first part.
Yeah.
So if dp dy equals dq dx, that doesn't necessarily mean it's conservative.
Right.
If
Right.
it's not true, then it's not conservative.
That's right. This is saying is that, if you're a conservative C1 vector field, then you know this is going to be true. But it's not saying that if this is true, then you're a conservative vector field.
Okay.
Okay, you see, right? It's like saying, if you are Chinese, then you're a human being, right? But it doesn't mean that if you're a human being, then you're Chinese, right?
Okay.
But it means that if you're not a human being, you're certainly not Chinese, right? Okay. Okay, but in fact, it's true. If you're a human being, in fact, it's true. You're Chinese, if and only if you're a human being. That's what the second theorem says, effectively, right? That, in fact, right, that if you're, if this holds, then the field must have been conservative. Okay, so it's true in both directions. Right, so this second theorem gives you the opposite condition. Okay, gives you the opposite fact, but only in the case of simply connected regions. Okay, and simply connected simply means, roughly speaking, means no holes. Okay, so you're not in some region that, like an annular, you're not in some sort of annular region. That's all that it means. Technically speaking, it means that whenever you have a loop, simply connected means that whenever you have a loop, you can draw the loop in until it vanishes in your world. So you're not living on a world that has some big hole in the middle of it, right? In this world, you could have this loop, and you try to pull it tight, but you never drag it down to nothingness. Okay. So this second theorem says that in fact, this is a good way of checking if your field is conservative or not. It's not just that if it's not true that it's not conservative. If it, in fact, further, if it is true, then you are conservative. Okay. So this condition, at least, this fact, at least under these conditions, is the same thing as being conservative. Okay. And the proof of it is the proof uses something called Green's theorem, which we haven't gotten to yet. But we'll talk about Green's theorem next time. Okay. So what we've gotten today are basically a bunch of things that are consequences of being a conservative vector field or equivalent to being a conservative vector field under certain conditions. Okay, it's not that all these things are the same, but under certain conditions, one implies this, one implies the other, or the other implies the first. Okay, so these are all related ideas. Okay, that's it for today. Yeah, so the homework problems will basically be, is this field conservative? What is the integral of this field from here to here? And you'd say, oh, look, the field is conservative, so I only need to take the difference at the endpoints. And you'd show that it's conservative by using one of these tricks.